All right, people ready to start? I'm just noticing we have, by the looks of things, like 10 empty seats, which, yeah, I'd agree. I think that everyone that was scheduled is not here, obviously. I'm going to just not do anything about that today and then check again on Friday and see where we're at and maybe rethink that, because I don't like the idea that there's people that want to be here, that could be here, but obviously the way the system works. I also don't want to like overbook the room and have people have too many people and then have to send somebody home. What would be great is if there was like an empty classroom right now nearby where people could go and kind of be like on deck and they could do the Teams thing there, but then I could like last minute call them up. So that's a thought. Anyway, just a notice too, if you are scheduled to be here on a certain day and you don't think you are going to make it, like, yeah, obviously, like if you're sick that morning or whatever, like, please don't come. But if you know well in advance that you can't make it that day, just let me know and I can let somebody else on the list know that they're welcome to come if they want to. Okay, so we are right now in chapter 2. We're talking about intermolecular forces. We just kind of started this last class. And just very briefly, we're going to go through and kind of review the different types of intermolecular forces and then get into what we called organic functional groups last class. And I think last class we did cover ion-ion forces, and those, you know, these would just be examples where you have two ions that are, say, in solution or nearby each other, and these ions, if they're opposite charge, will attract each other, and that's a very strong force of attraction between particles. If we have a polar molecule, like you can see right there, that molecule is acetone, and that's polar because oxygen is more electronegative than carbon. So you have this imbalance in charge between those two atoms, slightly negative end on the oxygen, slightly positive end on the carbon. Sometimes we also use these dipole arrows. The negative end of that polar molecule will be attracted to oppositely charged ions. So the negative oxygen would be attracted to a sodium, and you could imagine the positive end on the other side could be attracted to something like chloride, something with a negative charge. So ion dipole is another type. You see these a lot in biochemistry. A lot of biochemical molecules, biomolecules have a charge, plus or minus. So those become very important for those planning to take biochemistry later on. Dipole-dipole forces are kind of like the next strongest after ion dipole. This is when you have two polar molecules that will like to orient themselves so that the negative end of one molecule comes close to the positive end of another. And you can see this is, again, a molecule of acetone, which is used in nail polish remover. And the negative oxygen is attracted to the positive carbon in the next molecule. And this can extend kind of in 3 dimensions throughout a solution. And that kind of holds all the molecules together and, yeah, keeps it together in one phase. Dispersion is the next one. Dispersion is when you have a dipole that's not permanent. When you have a nonpolar molecule or a molecule that does not have a permanent dipole, what happens is these electrons, you can kind of think of them as big squishy clouds. We talked about this a little bit in previous class. And because squishy, they can be pushed around. And you can imagine in this molecule here where we have a molecule of bromine, Br2, what could happen is if you bring this close to, say, a dipole or an ion, what can happen is the negative end of this molecule will repel the negatively charged electron cloud around this nonpolar bromine, and it can kind of shove the electrons away from itself. And so what happens is there's this sort of imbalance of electrons around that Br2, that nonpolar Br2, and then what that does is creates what we call a temporary dipole. So that Br2 is not normally a polar molecule, but in this instant, it is. And so we have a positive end where the electrons have fled from, and we have a negative end where the electrons ended up, and you end up with a polar molecule, but it's only temporary. So we call this a temporary dipole. And all molecules with electrons can set up these temporary dipoles, and they can be set up kind of in any direction. And what they always do is they always lead to a very, well, not very weak, sometimes it's very strong, force of attraction between that dipole and that molecule right there. So this reminds me a little bit of a time I used to live out west. I used to live in Victoria, BC, and oh, sun just came out. I used to live in Victoria, BC, and travel a lot back and forth between Victoria and Vancouver. It's my girlfriend, she's married to her now, was living in Vancouver. So it's a 2-hour and 35-minute trip on the ferry. And I remember once, if you think of the ferry where you have, I don't know how many people are on the ferry at once, like say 1,000 or 2,000 people, and they're kind of distributed randomly over the boat. And I remember us sitting there just passing time, and the announcer came on over the speakers and just said that there was a pod of orca whales, killer whales, off on one side of the boat. And what happened is like every person who was on this boat kind of like shifted over to that side of the boat and just watched them as we went past. And then once you were past the pod of whales, everyone just kind of shifted back to their normal positions, randomly distributed around the boat. And I remember thinking at the time, like, is the boat going to tip? You get all those people on one side. It didn't. We were good. But this is what kind of reminds me of what's happening in this Br2 molecule. All those electrons are sort of evenly distributed around the molecule, and then something interesting comes by. This pod of orca whales, or acetone molecule in this case. What happens is rather than attracting the electrons, it repels them. They all shift to one side of the molecule. You set up this dipole, this imbalance, and then once the acetone molecule goes on its merry way, because molecules are moving all the time in solution, it shifts back the other way. Or it may shift the opposite way if a different molecule comes on the opposite side. So these electrons, think of them as a big squishy blob that are constantly kind of in motion. And anytime they're not perfectly evenly distributed, that molecule will have a temporary dipole and will attract other molecules. So you don't need a polar molecule like I've drawn here either. You can have two completely nonpolar molecules attract each other. They can induce dipoles in each other. And so this is a very important intermolecular force, in particular for nonpolar molecules that don't have dipoles, that don't have these other types of intermolecular forces available. All right, the next one I have is 5, hydrogen bonding. Hydrogen bonding, I kind of give it its own category. It's basically a subclass of dipole-dipole intermolecular forces, but there's some differences. Okay, it's a particularly strong type of dipole-dipole force. It's only available to molecules with OH, NH, or FH bonds. Fortunately, in organic chemistry, OH and NH bonds are super common. Okay, we see these all the time. FH is not common. There's only one molecule that has an HF bond. You know what molecule that is? HF. So HF, sure. HF, we're not too worried about that in biological systems because there is no HF in biological systems, or there shouldn't be. If there is, there's a problem. But the other ones, OH and NH, very, very common in organic chemistry. And what happens is it leads to these, the reason why OHs and NHs do hydrogen bonding is because the oxygen, there's a big electronegativity difference between the O and the H, or the N and the H. So you get a very strong dipole kind of set up, and that leads to very strong forces of attraction. And what we see is that molecules that have hydrogen bonding typically have properties that are different from molecules that don't. So typically they have very high boiling points. Think of something like ethanol has a boiling point of like 79 degrees Celsius, or if you get rid of that OH, it's a very small molecule, might be even a gas at room temperature. you will see, especially if you're taking biochem, example after example after example of molecules where hydrogen bonding is super important. DNA is a great example. You know how DNA is a double strand? Like those two strands are held together by hydrogen bonding. So we're going to see lots of examples. One thing that happens is molecules with hydrogen bonding will often hydrogen bond with water and are therefore very soluble in water. And again, in biochemistry, you want your biomolecules to be soluble in water, because if they start precipitating out of your cells, you're going to have an ugly situation. So vodka is like a 40% solution of ethanol in water. Ethanol just has this structure here. And so it can hydrogen bond with water, which gives ethanol, first of all, a high boiling point, second of all, high solubility in water. And so these are two features that are going to be very important for molecules that we see. I'm going to just say one more thing about this, and I want to just pop over to here. We talk about molecules with OHs and NHs, for example, having the possibility to do hydrogen bonding. And R here, R is a shorthand we often use in organic chemistry, just to mean the rest of the molecule. So anything that has an OH group or an NH or an NH2, for example, can do hydrogen bonding. But you can also have molecules that can engage in hydrogen bonding that don't have OH or NH. They can behave instead as hydrogen bond acceptors. So here's an example. You guys know about the Instagram account that I'm putting questions up. You've heard of it, seen the emails. There's a question that was maybe today or maybe yesterday, but it had 3 molecules, and you had to say which one can act as a hydrogen bond acceptor. So if you have molecules that just have an oxygen or a nitrogen in them with no OH or no NH, they can still engage in hydrogen bonding by accepting an OH or NH from something else. So the molecule, the answer to the one that was on Instagram was this molecule, and that has 2 oxygens, each with 2 lone pairs. It can hydrogen bond like this. This molecule is called dioxane. And dioxane is completely miscible with water, meaning you can mix it with water in any proportions and it will always dissolve, always form one solution. It doesn't separate into layers. Many organic solvents do separate into layers when you mix it with water. But this one, because it's such a good hydrogen bond acceptor with water, you get this hydrogen bonding interaction, even though that partner of the hydrogen bond doesn't have an OH or NH. The other partner, water, does. So one of them has to. And if you had a pure solution of just dioxane, it will not hydrogen bond. There's nothing it can hydrogen bond with because it needs an OH or an NH or an FH, although FH, super rare, as I said. It needs one of those. It needs a donor and it needs an acceptor. So the donor is the OH or NH. The acceptor is just any nitrogen or any oxygen that has lone pairs. And that's important for DNA, because if you look at DNA and you look at the hydrogen bonds between the DNA bases, there are atoms there that are acting as hydrogen bond acceptors that are just a straight up oxygen or nitrogen that don't have an OH or an NH. All right, so what we're going to do is go through kind of a survey of the functional groups or the different pieces of organic molecules that we most often encounter. And this is typically the ones encountered most often in biological settings, or maybe industrial or other applications, the ones that you see most often we're going to be talking about. The first class we call hydrocarbons. Hydrocarbons are just molecules with hydrogen and carbon only and nothing else. These are extremely important for industrial applications. Oil and gas are largely hydrocarbons, and We burn them for energy. We use them to make all sorts of products like lubricants, oils, or plastics, lots of things like this. So there's different kinds of hydrocarbons. We break them up into different classes. And the first one is called aromatic hydrocarbons. And aromatic is sort of it's a legacy name, I guess. When we hear the word aromatic, what we normally think is something that is fragrant or like smells nice maybe, or smells strongly. That's not what aromatic means in aromatic hydrocarbons. Maybe it did like 200 years ago or 300 years ago, but that's not the meaning we have for it now. It has to do with this alternating pattern of double and single bonds that you can see in a structure. So benzene is an example of an aromatic hydrocarbon. Remember, each of the 6 carbons, each corner here in benzene is a carbon. How many hydrogens are in a molecule of benzene? 6. Each corner, each carbon, has a hydrogen that's not drawn in, because this is a bond line structure. And we know it has 1 hydrogen each, because each carbon needs a total of 4 bonds, right? So there's a hydrogen here, hydrogen at each kind of corner as we go. Naphthalene is another example. Naphthalene is a compound that's mothballs, which I don't think people encounter mothballs as much as maybe once did. I think mothballs are, they're if you like store clothing or blankets or something for the summer, or I guess you'd store them in the summer, wouldn't you? There's a certain kind of moth that will like lay eggs on wool, and they'll eat wool. And so you put mothballs in and it'll kill the moths. But yeah, I've never met somebody in my adult life who's used mothballs. But hey, maybe there's still a need for them somewhere. These are other examples. These become very important, or aromatic molecules. First of all, aromatic compounds are super, super, super common in all applications, in biology and everything. So you're going to see these quite a bit. If you're doing organic 2, you'll learn why these kinds of compounds with alternating single double bonds in groups of 6 they have sort of like a special stability. They become very, very stable molecules. The other kind, if it's not aromatic, we say it's aliphatic. Aliphatic is just sort of every other hydrocarbon that's not aromatic. And these are broken into 3 types: alkanes, alkenes, and alkynes. Alkanes just means that all of the carbon-carbon bonds are single bonds. Examples you can see here are octane, which is a component of gasoline, butane, which is in lighters, and propane would be another example. It's in your barbecue. All carbon-carbon single bonds. These are very nonpolar molecules because, I mean, there's no electronegative atoms at all in this molecule. It's all just carbons and hydrogens, neither of which are very electronegative. If you have 1 or more double bonds, we call it an alkene. Alkene just means there's a double bond somewhere in the structure. Sometimes we use the word unsaturated to describe an alkene or an alkyne. If it's an alkane, we say it's saturated. It means all of the carbons have the maximum number of bonds that they can make, maximum number of single bonds. Ethylene and propylene, the correct IUPAC names for those are ethene and propene. These are used to make plastic primarily. Polyethylene comes from ethylene, and polypropylene comes from propylene. Alkynes have 1 or more carbon-carbon triple bonds. So acetylene is an example here, and it's a carbon-carbon triple bond. In this molecule of acetylene, how many hydrogens do we have? Yeah, there's 2. Because there's a carbon there with a hydrogen, and there's a carbon there with a hydrogen. Acetylene is used as a fuel, not to like heat your home. It's too expensive for that. It's used in welding a lot, and that's because it burns with oxygen to make a very hot flame. So you can use it to weld materials that you can't use other fuels for. And this is just a super random alkyne. What's the hybridization of the carbon in hexyne? Say right there. Just sp. Yeah. What's the bond angle here? 180. Yeah. Good. How about propene up here? What's that? What's that hybridization? That's sp2. How about this one? Also sp2. And how about this one? That one's sp3, all single bonds. Final question, propene. How many hydrogens are in a molecule of propene? We know it's C3 something. 6. So we have 1, 2, 3 on the carbon on the left. 4 is in the middle, CH, and then on the end, 2 more. C3H6. Great. Alkanes, alkenes, alkynes. These are, by and large, nonpolar molecules. And as a result, the most important, or maybe only, intermolecular force that these guys have is dispersion forces. Induced dipole, induced dipole. It's a type of dispersion force. So for this reason, these things don't typically dissolve in water. And, you know, oil and water classically don't mix. And this can have important benefits and drawbacks for use of these particular molecules. You want to make sure you're using them in the right situations. One thing you guys, I don't know how the labs are going to look this year, to be honest, but one of the labs that is classically done is called a liquid-liquid extraction, where you have 2 liquids mixed together that don't dissolve in each other. So typically a water layer and maybe like an oil layer. And what you can do is, if you put something in there, you can extract a nonpolar substance out of water into the nonpolar layer, taking advantage of the fact that these things don't mix with each other. Okay, so these hydrocarbons, we sometimes think of these as like the backbone of molecules. Essentially, all organic molecules will have carbons and hydrogens, and then you can think of pretty well any molecule as a hydrocarbon with decorations on it. Okay, so it's got carbons, it's got a carbon-carbon skeleton maybe. There'll maybe be carbon-carbon single bonds, double bonds, triple bonds, maybe aromatic groups in there as well. But then everything else that's on that carbon backbone or skeleton, we're going to call functional groups, or think of them as like the decorations, right? If you strip them all off, you would just have a hydrocarbon. Typically, in molecules, carbon-carbon single bonds, very strong, very difficult to break, fairly challenging to make as well. And so a lot of the chemistry we're going to be learning this semester is modifying those decorations, modifying those side chains, those functional groups that may be on our molecules. Sometimes we abbreviate them as R, meaning the root of the molecule. And these are some common carbon backbones or groups that we often see. We kind of give special names to a lot of these. We have CH3 with something attached. So let's say the something attached was an OH or some non-carbon group. Say it was NH2. We would call the carbon part of this molecule methyl. If you have 2 carbons in a row, CH3, CH2, ethyl. And if you have 3 of them, call it propyl. Here we have 3 as well. It's like propyl, but instead of that X group being on carbon, the end of the chain, it's on the middle carbon in that chain. And in this case, it's still a propyl group, but we call it an isopropyl group. Or more correctly, we call it a 2-propyl group, because it's on carbon 2 of the chain. Other common ones here on the right side, we have a vinyl group. A vinyl group is a carbon-carbon double bond with something attached. So when you hear the word vinyl, what do you think? Like vinyl records, yeah? Or like vinyl siding or vinyl flooring. Those are all made out of the same material, which is polyvinyl chloride. And polyvinyl chloride is made from vinyl chloride, where the X group is a Cl. And then this is made into a plastic. And the plastic is called vinyl, even though there are no vinyl groups. The vinyl part of polyvinyl chloride disappears after the plastic is made. There's actually technically no vinyl groups, chemically speaking, in vinyl. It's just made from vinyl. If there's a 6-carbon ring alternating double single bonds, we call that a phenyl group. If there is the same group with a CH2 before the X, we call that benzyl. And we have dozens and dozens of these sorts of names, and we're not going to go through them all and make you memorize them all. The ones that you see on the left side, probably yes, you will have to memorize those, but you will see these quite frequently. Methyl ethyl propyl, isopropyl or 2-propyl, you'll see quite a bit. Alkyl halides. So this is looking at now carbon backbones with something else attached. We'll be dealing a lot in this course with alkyl halides. Alkyl halides are carbon backbones with a halogen on there somewhere. Halogens are anything in row 17, not row, column 17 of the periodic table. So what's the top element in row 17 of the periodic table? Fluorine, yeah, and then chlorine, then bromine, then iodine, and then nobody knows after that. Astatine is the next one. And what's the one after that? Is it like tennessine or something like that? I think I have a periodic table here. Let me find out. Yeah, tennessine. See that right there? 117. So you can see here row 17 on our periodic table here. The whole column, fluorine, chlorine, bromine, iodine, astatine, and tennessine. You never hear of astatine or tennessine in organic chemistry because astatine is radioactive, so we don't really use it. And tennessine is like only exists for like a fraction of a second and is made in particle accelerators. It doesn't really exist as an element on Earth that we can use and make compounds from. But the other ones, fluorine, chlorine, bromine, iodine, you will see a lot in this course. So we call them alkyl halides. And we classify alkyl halides as either primary, secondary, or tertiary, and this will also be important in this course as well. So what that means is if you look at the atom, the carbon, that is bonded to the chlorine or the halogen, whether it's bromine or fluorine or whatever, look at that carbon and count how many bonds it makes to other carbons. So in this one, ethyl chloride, it's bonded to one other atom, which is the one I just circled. And so we would say that this one is primary, 1, because it's bonded to one other carbon. Isopropyl chloride, the second example, the carbon that's bonded to the chlorine has 2 carbons that are attached to it. So we call this one secondary. And this example that we have over here, the carbon that the bromine is coming from has 1, 2, 3 carbons attached. So we say this one is tertiary, or 3 with a little 0 there. Okay. Ethyl chloride used to be used as a recreational drug, I guess you could say, although ethyl chloride is a compound that it's a gas, it's easily compressed, and it's non-flammable, doesn't burn. And so people used to buy it in cans, compressed cans, to like blow dust out of electronics. And it was good because it wouldn't catch on fire. And but apparently people learned that if you inhale this, you can get a high. So you can't buy it for that reason anymore. I don't think. That's what it's called, duster. It's for dusting. Alkyl halides have halogens, which are electronegative. Particularly the fluorine, right? Fluorine is super electronegative. And as you go down, electronegativity drops. But there's still some electronegativity there. So if you look at an example, this is methyl fluoride. methyl chloride, methyl bromide, and methyl iodide. All of these have an atom bonded to carbon. All of these bonds will be polarized towards the halogen group. Okay. As you go from carbon to iodine, the bond gets longer and longer because the atom it's attached to is getting larger. And the bond strength gets weaker. Notice CF is actually 472, dramatically higher than CCl, stronger than CBr, and stronger than CI. This is going to become extremely important later on because we're going to be reacting these things. And if you want to do a reaction on something, is it better for it to have a strong bond or a weak bond? It's better to have a weak bond if you want the bond to break. So we'll be breaking these bonds, and what you'll notice is that carbon-iodine bonds will break way easier than carbon-fluorine, carbon-chlorine, and carbon-bromine bonds. Carbon-fluorine actually is extremely strong. It's extremely difficult to break a carbon-fluorine bond. And this is actually a problem because carbon-fluorine bonds don't really exist in naturally occurring organic molecules. However, they're extremely common in man-made organic compounds. And so what we get as a result is a lot of these compounds that are being made and eventually end up out in the environment somehow. And because those bonds are so strong, these compounds persist. They last a long time. So a great example is Teflon. Teflon is full of carbon-fluorine bonds, which are very strong. It's very unreactive. If you put Teflon, like a Teflon container or something, out in your backyard and buried it, you could probably come back in 200 and it's still there, like the same, right? Doesn't break down very easily at all. It's something we got to consider when we make things. Alcohols. Alcohols are like alkyl halides. They have an alkyl group, carbon backbone group, with an OH attached to it somewhere. So OHs are alcohols. Alcohols are classified the exact same way that we classify alkyl halides, as primary, secondary, or tertiary. So ethanol is a picture here. This is showing the total alcohol consumption per capita worldwide in liters of pure ethanol per year. So in Canada, we're, I don't know, average, I guess. And definitely, like, Europe's way higher than us. I think that's probably because in Europe, there's a much higher tendency for people to have wine with meals. And it's a lot cheaper there, right? I think maybe more people in Canada would have wine with meals if it wasn't so expensive. But anyway, the active ingredient of all alcohols that we drink is ethanol. It's got an ethyl group, a 2-carbon chain, and ethanol is a primary alcohol because the carbon with the OH has one other carbon attached. Okay. So alcohols or alkyl halides, primary, it can be secondary, or it can be tertiary. What if you just have something like this, CH3OH? This is the carbon that's bound to the OH. There's no other carbons attached, so it's not really primary. It's definitely not secondary or tertiary. That we just call methyl. So an alcohol can be methyl, primary, secondary, or tertiary. And what we find is, all primary alcohols typically react alike, and all secondaries react different way, but alike, and tertiary, same thing. It's useful for us when we get into reactions to remember these classifications that we have. Here's some secondary ones. Isopropanol, also called 2-propanol. Also called rubbing alcohol. This is alcohol that you can buy at the pharmacy. I guess it's probably its main use, maybe, as a disinfectant, right? This is what they would, if you get an injection, like a vaccine or something. They rub that stuff in your arm and it feels really cold. That's isopropanol typically, and isopropanol evaporates a lot more easily than water. And as it evaporates, it takes heat with it and it feels cold to us. Menthol is a nice big organic molecule. it is a secondary alkyl halide because if you look at the carbon with the OH, there's 2 other carbons attached. So we call it secondary. And then this is just some big, weird, random structure I drew. That's a tertiary alcohol because the carbon with the OH has 1, 2, 3 other carbons attached. Cool. Alcohols have OHs, so they have hydrogen bonding. That means they are typically soluble in water or have a higher tendency to be soluble in water. And they have high boiling points. So compare these 3 molecules, propane, fluoroethane, and ethanol. They all have roughly the same molecular weight within 2 of the average here. The dipole moments are 0 for propane, nonpolar. Fluoroethane, the actual number doesn't matter, but you can compare them to each other. 1.9 dBi. dBi is the unit that we use to measure dipole moment. Very high in fluoroethane because fluorine is very electronegative. For ethanol, it's 1.7 dBi, so it's not quite as polar as fluoroethane. That maybe makes sense. Oxygen is also not quite as electronegative. But look at the boiling points, right? Propane minus 42, very low boiling point, very weak intermolecular forces because all it has is dispersion and it's very small. So it doesn't have very many electrons, so the dispersion forces are quite weak. The other thing is, which we didn't talk about when we talked about intermolecular forces, is something called polarizability, which means atoms that are further down the periodic table have stronger dispersion forces because their electron clouds are squishier. Fluoroethane, its boiling point is only 10 degrees higher. So that big, strong dipole moment it has, which gives it dipole-dipole intermolecular forces, it made its intermolecular forces a little stronger, but really nothing to write home about, right? We gained 10 degrees. But then going to ethanol, look, it jumps up over 100. So going from something that's very polar to something that's polar with hydrogen bonding causes this huge jump in its boiling point and in its water solubility. So keep in mind, look for OHs and NHs when you're thinking about these sorts of things. High boiling points, why is that important? How good would it be to have molecules in our body that have boiling points of -32? Well, we have some. We have like oxygen in our bloodstream, attached to hemoglobin, of course. Some CO2 in there. But like, generally speaking, we don't want large amounts of gas-type molecules inside of our cells or inside of our blood because they can form bubbles and kill us. Not good. All right, we're going to continue our march through here. The next functional group we're going to look at are called ethers. Ethers are when you have an oxygen atom that is bonded on each side to a carbon. Okay, so you can see the oxygen here in diethyl ether. It's got a carbon on one side, a carbon on the other, and it's got lone pairs on the oxygen. Ethers in general can act as hydrogen bond acceptors. But not hydrogen bond donors. Why are they not hydrogen bond donors? What does it need to be a hydrogen bond donor? Yeah, it needs an OH or an NH. Or an FH. Can't forget about poor HF. But OH and NH is really what we're looking for here. Diethyl ether used to be used in surgery to knock people out. We have much better compounds than that too. I think this is also used as a recreational drug. If something can make somebody high, it's used. If you ever saw the movie Fear and Loathing in Las Vegas, or read the book, yeah, Johnny Depp, he goes on an ether binge in the movie. So there you go. Ethylene oxide is another one. This is kind of a funny one. It's a ring. And just think about that molecule for a minute, right? I'm going to just redraw it over here on the side. We have a carbon, carbon, oxygen, lone pairs on the oxygen. Each of these carbons has 2 hydrogens. What's the hybridization of these carbons? sp3. What's the bond angle here? Oh, wait. It looks like it should be 109.5 because it's sp3. But how are you going to make a triangle with bond angles of 109.5? If you have an equilateral triangle, what's the bond angle inside the triangle? 60. That doesn't look good, does it? So we make molecules, we can make molecules like this, even though, Vesper allows us to predict bond angles of 109.5, 120. This is under an ideal situation. We can make molecules that have weird bond angles. We can force it to be smaller or larger than what would be ideal. And a molecule like ethylene oxide actually is like just waiting to undergo a reaction and open up. It wants to relieve, it creates a lot of strain in the molecule when you squeeze those bond angles to be very different than the 109.5 that they want to be. So this will react like a hot dam, and it's used in epoxy glues. And if you put the right, did you ever use epoxy glues before? It's like glues that come in like 2 different tubes, and they're listless. They don't do anything unless you mix them together. When you mix them together, it kind of makes like a little paste, and then it'll say on the like containers how much time you have before the glue sets. I think there's some that are really quick, like it'll set in like a minute, and some maybe have 10 minutes. Depends how much time you need to work before it sets. But it uses not ethylene oxide on its own, but that with like a chain on the side and other things, and that it creates epoxy glues. So it reacts quite quickly. Amines, super common in biology. Amines are compounds that have nitrogen attached to carbon. Okay, typically with all single bonds. So yeah, amines can have 1, 2, or 3 carbons attached to the nitrogen, because nitrogen has a lone pair and you can have up to 3 carbons attached. Here's some examples. Cocaine has a nitrogen bonded to 3 carbons. Nicotine, you can see, has a nitrogen there. Putrescine and cadaverine. Guess where they get their names from? Yeah, they smell. They're produced when you have rotting flesh. So the smell of I know the smell well only because so where I live, garbage is only picked up every 2 weeks. And I made the mistake of having fish the day after garbage pickup. And it was hot in the summer, and oh my God, that composter, you could smell it for like 2 kilometers away. And it just smelled like, and it sat there for 2 weeks in the hot sun. Yeah. So these are amines. Amines typically have kind of a pungent, fishy smell to them. In fact, the amine that gives rise to the smell in fish, that's getting a little old, is this trimethylamine. And amines are very strong smelling. Okay. Now, something like cocaine and nicotine, if you make the molecule large enough, it has to be volatile. It has to get into the air before you can smell it. So yeah, those things probably don't really have a smell. And they're primary, secondary, or tertiary, depending on the number of carbon groups as well. Amines and ethers both can be hydrogen bond acceptors, but I guess amines can be hydrogen bond donors as well if there's an NH. Like you could have a CH3, N, CH3, H. This guy would be a hydrogen bond donor and a hydrogen bond acceptor, because it has a lone pair on the nitrogen, which makes it an acceptor, has an NH bond, which makes it a donor. But even something like this, triethylamine, can hydrogen bond with water as a hydrogen bond acceptor. Ethers we already looked at can be hydrogen bond acceptors. So if you look at water solubility, this guy, which is just pentane on the left, very, very low, 0.004 grams in 100 mils of water. Very, very low solubility. Stick an OH on there, and that jumps up to 7.7 grams. It dramatically increases the water solubility. That makes sense. OH hydrogen bonds can hydrogen bond with water, and that allows it to become water soluble. Notice that this ether is almost as good, not quite, but almost as good as the alcohol in terms of its water solubility, even though it has no OH. But that makes sense because water can be the donor, this can be the acceptor, and we can dissolve it. This amine, it's a hydrogen bond acceptor as well, 17.1 grams per 100 mils, so it's even better. Okay, so it can be a hydrogen bond acceptor only and still be very soluble in water, and this is important for a lot of organic molecules. All right, the next group of compounds we're going to be looking at have carbon-oxygen double bonds. And that carbon-oxygen double bond, just on its own, we call a carbonyl group. Carbonyl group just means a carbon-oxygen double bond. These bonds are typically quite polar because there's a big difference in electronegativity between carbon and oxygen. Okay? They're strong bonds, they're pretty short. Although that double bond, oops, I went too far, go back. That double bond, if you have a carbon-oxygen double bond, has one sigma bond and one pi bond. Which one of those two is stronger? Sigma is strong, pi relatively weak. So this can do reactions, and it often does do reactions, and it's often the pi bond that's reacting, or disappearing maybe in the reaction. So there's a number of different functional groups. About half of the functional groups we're going to look at have these carbonyl groups, and they all have their own behavior. So aldehydes are ones where you have a carbonyl group, C double bond O, with a hydrogen on at least one side. And so formaldehyde is an example of an aldehyde because it has the C double bond O and a hydrogen on at least one side, in this case, both sides. Vanillin is the molecule produced in the vanilla bean. And you can see it has a aldehyde group there as well, carbon, double bond, oxygen, and a hydrogen. Do you see any other functional groups in vanillin? What else has this guy got? It's got an alcohol right there. This is an ether right here. Carbon, oxygen, carbon. And what about this whole thing here? What's that? That's an aromatic ring. Benzene ring, aromatic. So this is nothing but functional groups, I guess you could say. A lot of functional groups here. This guy, cinnamaldehyde. Can you guess where this is found? Cinnamon, yeah. Smell this, it's like you're getting a super concentrated shot of cinnamon. It's got an aldehyde too. Carbon, double bond, oxygen with a hydrogen attached. What other functional groups does this have? Got aromatic. And what about this? Carbon-carbon double bond. We have a name for those too. Alkene. Okay, so this has got a couple of different things on there as well. When we start reactions, we're typically going to be dealing only with molecules with one functional group at a time, and maybe build up to some more complex examples that have multiple groups available. All right, here's some more examples. These ones are ketones. So ketones are just carbonyl groups, C double bond O, that has a carbon on both sides. So if carbon is on both sides, no hydrogens. If there's one hydrogen, then it's an aldehyde. If they're both carbons, it's called a ketone. And acetone is the simplest one because there's just CH3s on both sides. It's the simplest carbon atoms that you can have. Carvone is found in spearmint. You know when you get like mint candies? You know those candies you get and they're like white and they're kind of shaped like a football? And they're like either got red or green stripes. And like the red ones are really good and the green ones are awful. You like the green ones better? Ugh. Those ones are spearmint. Yeah, that's because it's got this molecule in it. The other ones are peppermint. Peppermint has, I think, methyl salicylate, which might come up later. Methyl salicylate is not a ketone, so I'm not going to draw it right now. But this has a carbonyl with a carbon on one side and a carbon on the other. What else it has is two alkenes, two carbon-carbon double bonds. This guy, big complex looking molecule. Notice how it has these 4 rings, A, B, C, D. We call that ring system of 6665 in that exact pattern, the steroid skeleton. So many hormones in the human body have that same backbone. Like you find that, well, cortisol, you find it in estrogen, the multiple estrogen compounds. You find it in testosterone. You find it in cholesterol. You find it in a whole bunch of different biomolecules. Cortisone has a bunch of ketones in it. They're all labeled there in red. They all have carbons on both sides. What else do you see in this compound? It's alcohol, 2 of them. Is that it? Alkene. Yeah, it's an alkene right there. Notice that like this OH here, the way I drew it with the sort of dashed bonds to it, why did I draw it that way? Yeah, it means it's going backwards inside the page, right? It's going away from our eyes. And you can see I used a wedge bond here to denote the opposite, that methyl sticking out towards us out of the plane of the page. I would love to keep going, but we ran out of time. So I'm going to stop today's class. I'm going to pick up where we left off next time, which was aldehydes and ketones. So you guys have a wonderful day, and we will pick this up next time.
Thank you.